Testing, testing, 1, 2, 3. Testing, 1, 2. Alright, hey guys, this is Albert, aka Avatar Abel, and today we are going over error checking code. Now, before we get into the video, make sure to smash that like button, subscribe, turn on post notifications, and go comment down your favorite dessert. Alright, now without further ado, let's get on with the video. So, as I mentioned before, this topic is error checking code. And here's just a quick introduction. A binary code is a set of binary vectors of the same length called code vectors. And the process of converting a message into code vectors is called encoding, and the reverse process is decoding. Now, suppose we encoded a message as a set of binary code vectors and sent them across a channel such as a radio transmitter, telephone line, fiber optic cable, or CD laser. Now, those channels may be noisy, which can cause errors. For example, some of the zeros and ones in the code may be changed as a result. And just some ways that code errors may be introduced include electrical interference, competing signals, or dirt and scratches. An early example of error detecting code was the use of binary codes of length 3. So if we were to transmit code about direction, we could assign the direction up as 0, 0, 0, down as 0, 1, 1, left as 1, 0, 1, and right as 1, 1, 0. This code can detect any single error. For example, if down was sent as 0, 1, 1 and an error occurred in one component, the receiver would read either 1, 1, 1, 0, 1, 0, or 0, 0, 1, none of which is the code vector. So we would know that an error had occurred, but not where. But we can ask that the code message be retransmitted. The message may itself consist of binary vectors, which is just 0 and 1s. In this case, it was a parity check code, and it was created by adding an extra component called a check digit to each vector so that the number of ones is even. So an example would be if a message was 100101, it has 3 ones, which is odd, and so the check digit would be 1 in order to make it even. And so the new code vector would be 100101 with the extra 1 added at the end. And note that a single error can be detected since it would cause the parity to change from even to odd. So in general, a message can be a binary vector b from b1, b2 all the way to bn in the nth dimension with base 2. Then the parity check code vector would be b1, b2 all the way to bn, but there would be an extra d at the end and the n plus 1th dimension. The check digit d is chosen so that the sum of all the components would be 0 in base 2. Parity check codes are a special case of check digit codes, and codes using m-ary vectors are called m-ary codes. So one simple application is universal product codes, or UPCs. They are found on the back of merchandise. They're just those simple barcodes. The black and white bars, they're scanned by a laser at a checkout, and they correspond to a 10-ary vector, U from U1, U2, all the way to U11, and then D, which is the check digit, and it's length 12. And the first 11 components form a vector in 11 dimensions with base 10, and they give manufacturer and product information. And the last digit D is chosen so that the product C times U is 0 in base 10, where C is the vector 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, 1. So in other words, you can kind of group like terms, and you'll see that 3 times the quantity of U1 plus U3 plus U5 plus U7 plus U9 plus U11 plus 1 times the quantity U2 plus U4 plus U6 plus U8 plus U10 plus U12 plus D is 0 in base 10. So it's a multiple of 10. The UPC will detect all single errors and most transposition errors in adjacent components, since C times U is not equal to 0 if a component was changed. So here are some example problems. The first one is to find the parity check code for the binary vector U equals 1, 0, 1, 0. And the solution is that since the number of 1s in U is even, the check digit must not be 1. And since it's in binary, the only valid digits are 0 and 1. We can't use 1, so we have to use 0. So the parity check code is 1, 0, 1, 0, 0. Second problem. Determine, it shouldn't be a D there, if an error occurred in the transmission of a parity check code vector V if V equals 1, 1, 1, 0, 0. An error will occur if the number of 1s is not even, and there are 3 1s, so that means an error has occurred. Example 3. Find the check digit D in a given UPC. 42069, 42069 for D. From the example on UPCs, we know that to use this equation, which is just 3 times all the odd components and 1 times all the even, except for the last one, which is D. And plugging in the numbers, we find that this results to 96 plus D equals 0. And since 96 plus D has to be a multiple of 10, and the next multiple of 10 starting from 96 is 100, then 96 plus D is 100, so D has to be 4. Another way would be doing 96 mod 10, and modulo is just finding the remainder when dividing 96 by 10. So 96 mod 10 would be 6, and you could just do 6 plus D equals 10, so D would be 4. Now, an application not found in the textbook that I found was error detection and correction onboard nanosatellites using Hamming codes. So just a brief introduction. Satellites, they have many applications, with Earth observation being a primary application. And with constant improvement, the captured data becomes more sensitive and valuable, and that results in a need for security and privacy. And it has been proven that satellites are susceptible to unauthorized intrusions, and they could be hacked. So cryptographic protection can be implemented to provide protection against these intrusions. So Hamming error and correction code was first introduced by Richard Hamming in 1950. It is a linear block detection and correction scheme that adds additional parity bits, also known as R, to the sent information, which is K. The code word bits can be calculated according to n equals 2r minus 1, and the amount of information data bits is calculated by k equals 2r minus r minus 1. So using a parity check matrix and a calculated syndrome, this scheme can self-detect and self-correct any single event effect, or SEE, error that occurs during transmission. Once the location of the error is identified and located, the code inverts the bit, returning it to its original form. A generator matrix, which is G, is used when encoding the information data to form the code word. G forms one of the foundations on which the Hamming code is based. G is defined as the combination of the identity matrix I of size k by k and a submatrix P of size k by r. And then here's just a little equation. G k of n equals a matrix where it's I k by k and P k by r. And a parity check matrix, which is H, is used when decoding and correcting code word in order to extract an error-free message. God, I have so many spelling errors. H forms one of the foundations on which the Hamming code is based. H is defined as the negative transpose matrix submatrix P of size K by R and the identity matrix I of size R by R. And then the equation for that's down here, which is H R by N is negative P transpose K by R and I R by R. So the relationship between G and H is such that G times the transpose of H is equal to 0. And here are some examples of Hamming code. So in this table, this was an early example of Hamming code, and here's the algorithm that gets all these values, such as block length, message length, and distance. And this is the general layout of Hamming code, where you give an input, which goes to the encoder, and it uses the generator matrix that I talked about earlier, G, to calculate the code word. And when it's put into storage, there could be some errors caused due to space radiation. But then you go to the decoder, which uses the parity check matrix, which was H, and it locates and corrects errors. And then you just put it back into the output, and there's no errors. So you give an input with no errors, and you get an output with no errors. And here are my works cited page. All right, that pretty much wraps it up. So yeah, see y'all next quarter.